Welcome, I'm Maciej, and I'm going to present the results of our work on high-performance multipath routing in low-diameter network topologies. The interconnect is an important part of compute centers, relevant for both low construction cost and for high performance. Let's first take a look at the setting that we are going to use in this presentation. In such a topology that we are going to consider, we have a set of routers, and each of these routers is attached to a set of servers, also called endpoints. And these routers form some topology of router-to-router links. We're going to use the following symbol in the stock to refer to a router, a single router with its servers. Recently, several new topologies have been proposed, for example, Dragonfly, HyperX, Jellyfish, Slimfly, or Expander. They all share the property of having low diameters. Diameter is the longest of the distances between pairs of routers. Before we proceed, let's first analyze briefly why do we care about these networks, because we already have powerful designs like Clos or fat trees. Well, we care about these new topologies because they are in many cases more cost effective than fat trees. They come with high energy efficiency, and also they have low latencies. The big question is how to route these topologies to ensure high performance. Before we proceed, let's first briefly summarize routing in fat trees. High-performance routing in such topologies is really facilitated by certain fundamental properties of these networks, namely, they have a multiplicity of paths that are shortest and have the same length between different pairs of endpoints and pairs of routers. For example, if you take a look at these two routers indicated with the blue color, they can communicate with each other using not just a single, but two paths that are shortest and that have different lengths that are indicated with the red color. So for example, to send packets from the left to the right, the router on the left can split these packets into two portions, thus reducing congestion in the topology, possibly reducing congestion in the topology. This property means that we can use established techniques such as ECMP, a plethora of other designs that are really based on this assumption that the given topology has some diversity of shortest paths between pairs of routers. But the question is, do we have something similar in low diameter network? We don't really know, and this is the big question, how to route these topologies using multipathing so that we have maximized performance. Before we proceed, let's really first take a look at why do we even care about multipath routing in the first place. The problems that we want to tackle with multipathing are the following. Let's take a look at some example topology. One of the problems we are going to tackle are the so-called flow collisions. So once we have the topology, we're mapping some workloads. We are mapping pairs of communicating endpoints to the routers. What may happen is that we map one pair of these endpoints to such a pair of routers in such a way that we don't really have any collision. So there's like one pair of endpoint attached to one pair of routers, and then they can just freely communicate. But what can also happen is that in the mapping process, we map two pairs of endpoints that are communicating with each other to the same pair of routers. And this could cause one collision because, assuming deterministic routing, the flows between these two pairs of endpoints are going to follow the same path in the network. We can also find a case where we have we can also find a more extreme situation with two collisions, etc., etc. And here, multipathing would help because with multipathing, we could reroute these colliding flows in such a way that they use different paths somewhere in the network, minimizing congestion. But the question is, we may have different traffic patterns that we map to the topology, and the question is, how many such alternative paths we need to accommodate such collisions for different traffic patterns? This is really the first question that is forming the first part of the talk. Then in the second part, we are going to ask a question. Once we know these requirements, how many paths we need in the topology to accommodate flow collisions, there's the second question. For these different low diameter networks, do they have enough such paths? Then once we know the answer, there's a question how to use this answer to develop high performance multipathing routing architecture for these networks. So first, let's analyze these requirements for the topology coming from the workload. Here in these plots, the plot on the left is dedicated to diameter 2 topologies like slimfly. The plot on the right represents topologies with diameter 3, such as dragonfly. Different data series correspond to different workloads. And on the x-axis, we are showing the number of flows that are that we have for some single fixed router pair, right? So for example, one here, the number 1 corresponds to a router pair that has no collision between them because it has only one flow. Number 2 would correspond to this case that we saw with one collision and thus two flows occupying the same path between the same router pair. And now on the y-axis, we are plotting the number of such router pairs that are experiencing a given scenario that they have, for example, only one flow between them, or two flows, or three flows. And now we can see some interesting things. So first, of course, once we move beyond number 1, once we move to the 2 flows per router pair, we encounter the region with collisions. And the second interesting thing is that there are two distinctive parts of these plots. So these vertical bars are dividing these two plots, and on the left side of these bars, we can see that there is some large number of router pairs having a given scenario, and on the left there are very few such router pairs. So what we can see here is that once we move beyond 4 flows or beyond 3 collisions, there is really not much pairs with such a scenario. This is really an interesting outcome because it really tells us that that out of all the pairs of routers that have some collisions, less than 1% really have 3 or more colliding flows, and really this really only happens, this small amount of routers with these collisions only happens for heavily oversubscribed traffic patterns. For the non-oversubscribed traffic patterns, this doesn't really happen at all. So that's a nice property. It gives us some motivation to move forward. And also the outcome is robust because it really is generic for different workloads and different topologies. This means that our first key insight is that we need at least 3 disjoint paths per router pair to handle almost all colliding flows, considering also heavily oversubscribed workloads, and really all flows if we consider workloads which are not oversubscribed. Now, once we know this requirement, the second question, the second part is, do we have that many multiple paths in such low diameter topologies that we consider? Let's start with shortest paths. Each of these small plots is a histogram, and in each of these plots is dedicated to a different network topology. Fat tree is on the left as a baseline, and then all the other low diameter ones are on the right. On the x-axis of each of these plots, plot the number of shortest paths that we have between some router pair, and on the y-axis we plot the percentages of router pairs that are connected with that many different shortest paths. First thing that we can see is that what we actually expect from a fat tree. In a fat tree, 100% of all the router pairs are connected with more than 3 disjoint different shortest paths. However, this is no longer the case for low diameter networks. For some of them, like Expander, slightly around somehow less than percent of router pairs are connected with more than 3 disjoint shortest paths. But for others like Dragonfly or especially HyperX and Slimfly, very few or no router pairs are connected with 3 or more different shortest paths. And that's really bad because this means that we cannot really hope to use established techniques like ECMP or others, which are really based on the assumption of the multiplicity of shortest paths in the network. So what do you do about it? Well, let's take a look at how non-minimal paths behave. As we consider non-shortest paths, we are introducing one more parameter in our analysis, namely the length of the non-shortest paths, which can be essentially anything. And this means that we also have this one more parameter that makes the plot more complex. That's why we are going to focus only on a small part of it. One row, so each of these plots is again a histogram, and one row corresponds to a specific topology. One column corresponds to a given value to a given length of the non-shortest path. Let's focus on Slimfly. And then on the x-axis, we are again plotting the number of different non-minimal paths between a router pair. And on the y-axis, we plot the fraction of router pairs connected with a given number of different non-minimal paths. What we can see is that the 2 hops which really corresponds, 2 hops are the diameter of Slimfly. This tells us that there is really little or no diversity of paths at that length. So nearly 100% of router pairs are connected with only 2 different paths up to that length. But once we move to the length that are larger than diameter by at least even 1, we can see that nearly 100% of router pairs are connected with a large number of different non-minimal paths. The same stands for other topologies. This is our second key research insight related to the structure of these networks. Yes, we do have enough path diversity in low diameter networks to accommodate flow collisions for different traffic patterns, but only if we consider almost minimal paths, where almost means the length of the shortest path in this topology plus 1. Let's summarize. To have now answers to these 2 first questions. The answer to question number 1 is we need at least 3 different paths somewhere in the topology per router to accommodate flow collisions. And the answer to the question number 2, if we have that many, yes, we do, but only if we consider non-minimal paths. Now let's see how to use these insights to construct a high-performance routing architecture for these topologies. The central idea and the central design in the whole architecture that we call FatPaths is the so-called layered routing protocol. Let's take a look at an example. We take some default topology. In this example, we grab a Slimfly. So this means that paths are going to traverse at most 2 hops in the default topology, where we just route in a default way. We have some communicating scenario of 2 endpoints. Now in our layered routing protocol in FatPaths, divide the links in this default topology into subsets that we call layers. And one layer is created by removing some fraction of the links, for example, using random uniform sampling. We do have more advanced schemes, but this one is enough for the purpose of the representation. This means that we grab the default topology, and each time we create a separate layer, we sparsify this layer by removing some fraction of links. This creates topologies which are just much sparser. And now this means that and now the key idea here is to spread the communication between 2 endpoints that we saw before in the default topology across different layers. Now, as these layers are usually going to be different, these are going to be usually different paths in each layer for the same pair of endpoints. On the other hand, really the other central idea in the protocol is that in each of these layers we want to route minimally, because we know all these established routing protocols that work for minimal routing, and this makes our life easier. But the whole point is that this is only minimal routing within a single layer. But speaking globally for the whole topology, considering all the links, that's going to be usually a non-minimal path. Now, both the number of these layers and the sparsity are parameters that can be set by the user, and they are usually based on, for example, what the hardware offers in terms of, because the layers have to be somehow implemented in the hardware, and now basing on these hardware capacities, we can tune the number of layers to match the hardware capacities. And in terms of the sparsity, we also conduct an analysis that really tells us how to select the sparsity to maximize the performance. But as we can see later, for now, what we just want to underline is that this layered design enables multipathing because different layers enable encoding different paths. What you can probably already realize is that this all looks very static. And this is actually quite bad, because in real life, we need some adaptivity, some load balancing to react to congestion. So in the second part of our lecture, we propose load balancing for low diameter networks using flowlets. The central problem in this load balancing for these topologies is that, again, we may have to load balance traffic over paths of different lengths. So we use an existing mechanism called flowlet. It was developed for a different setting, and a flowlet is a sequence of packets within one flow that is separated from other flowlets flow by sufficient time gaps in such a way that there is little or no reordering of packets at the receiver. And now in FatPaths, our idea is to for the created layers, and once we have some communication between 2 endpoints, to send these flowlets across different layers in order to use different paths. What is really interesting about it is that this will enable us to use very simple load balancing. So namely, once there is some congestion at the source detected using some scheme that we use, detect this congestion, the router simply stops sending packets on a given path, and thus it kind of finishes sending one flowlet, and then selects randomly a different path by selecting a different layer, and starts to send the next flowlet on this next path, on this next layer. The size of these flowlets is going to change automatically because this is really guided by the topology, by the conditions in the topology. So once we hit more congestion, we are going to spread these flowlets over more paths, because we are going to sooner detect congestion when sending these packets, and this means that we are going to spread this traffic more uniformly, reacting to higher congestion. But if there is little congestion, we are going to keep sending packets on fewer layers because there is smaller chance that we are going to hit congestion and start sending over different path in a different layer. Now we do have many more design details, such as how to redeploy layers with mechanisms such as VLAN, how to create layers, how to populate forwarding entries, and also we do have details of the flow control mechanism in FatPaths. All these things are in the paper, and what we really would like to underline is that the proposed layered routing on one hand enables easy encoding of this multiplicity of shortest and non-shortest paths in low diameter networks, and on the other hand, it enables simple and robust load balancing based on flowlets. The evaluation, we want to answer two questions. Question number one is, can we get more performance on low diameter networks than on fat trees by using FatPaths? The question number two is, do we have more performance from FatPaths than from existing routing schemes on our targeted topologies? The setting is the concrete setting, we pick Ethernet, and this is really the result of one more analysis that we did. So we analyzed recent top 500 lists, and we realized that more than 50% of the systems in these lists use Ethernet. On the other hand, they are all consistently less efficient in their link-back efficiency than other systems based on different interconnects like InfiniBand. And this way we can enhance the design of as many systems as possible by as much as possible. Now in setting number one, we call the setting the bare Ethernet setting. So here we only consider Ethernet but with no TCP. And here the main baseline that we have is NDP, a recent scheme targeted for fat trees. Setting number two, we use the full TCP setting, where we consider two main baselines that come with different load balancing, ECMP for static load balancing and LetFlow for recent adaptive load balancing. Let's start with the bare Ethernet setting. As the traffic pattern, we pick stencil that stresses interconnect by causing a lot of flow collisions. Now, each of these plots is dedicated to a specific single topology. On the left, we have fat tree. This is different from all the others because it stands as a comparison baseline with different properties. On the right, we have all the considered low diameter networks. We skipped jellyfish because it's really similar to Slimfly. Now, on different data series correspond to different routing protocols. So circles correspond to FatPaths, and they are only running as expected on low diameter networks. And triangles correspond to the NDP baseline that we are running on both fat trees and on other topologies, just as additional comparison point. And then we have two types of data series. So the solid lines are the mean performance results, and the dotted lines correspond to the best, to the worst, to the bad cases. Now on the x-axis we plot flow sizes. So we are sending plots of in different experiments. We are sending flows of different sizes, and on the y-axis we are plotting performance expressed in throughput per flow. And now this means that these solid lines are going to correspond to the mean throughput across different communicating flows, and these dotted lines are going to correspond to the 99 percentile of the worst performing flows. So this will show really the bad cases, the bad cases for communicating pairs in the topologies that are suffering some form of performance loss. And the first insight that we get is that in comparing different topologies with and their best performing schemes on each of these topologies, you can see that some low diameter networks like Slimfly or HyperX using FatPaths can outperform the performance of fat trees using NDP by around 2x. And this is happening both for the average cases and for the bad performing cases. The second observation is that when comparing routing schemes within a single topology, for example, when comparing NDP and FatPaths within for Slimfly, there is a huge gap. So there is a huge improvement on these topologies when using FatPaths that explicitly uses non-minimal paths, and NDP, which is really oblivious to these paths and only assumes shortest ones. In the next plot, we are going to show example data from the full TCP setting. So here again, we are on the x-axis, but there is now much more data. So let's maybe focus only on Slimfly. On the x-axis, we are showing the size, again, the size of the flows. On the y-axis, we are showing the performance, but this time expressed in the speedups of the completion times of different flows. And again, we are plotting two types of results. So the bars correspond to the mean speedups, and the data, the single data points correspond to the best performing pairs of routers. So this is now the 99th percentile of the slowest completion times. And what we can see is and also we compare four different baselines here. So we compare two baselines for FatPaths. So one baseline is FatPaths with the sparsity of the layers equals to 0.6. So we remain only 60% of the edges in each of these layers. And out of curiosity, we also analyze the results for FatPaths with rho equals 1. So this is FatPaths that really comes with full layers. So there is no way to actually route anything on non-minimal paths, because they just don't exist in these FatPaths, because we take full layers from the original topology. And then we consider the traditional TCP with the ECMP and the LED flow load balancing. What we can see is that only FatPaths with this significant sparsity of the layers is having significant performance improvement over all the other baselines. So this happens both for the average cases and for the bad performing pairs of routers. And this really illustrates that these non-minimal paths are the key to high performance on the network, because we are better here not only than ECMP and LED flow, but also there are similar performance improvements over the FatPaths that is really oblivious to these non-minimal paths. You have much more data. For example, we have detailed analysis into how these different parameters of FatPaths, like number of layers and sparsity, impact the performance. Also more details about the behavior of different flows and scaling results for much larger networks, even up to 1 million of endpoints. They all confirm our outcomes from the previous slides. And there is even much more data in the technical report and also in the paper about other aspects of path diversity, other metrics that we introduce for this path diversity analysis. We also have full theoretical investigation, as well as a supporting survey about multipathing in different routing architectures. So the main takeaway message is that the FatPaths architecture enables high-performance routing based on multipathing and low-diameter networks. To show this, we first conduct an extensive investigation into the path diversity in these topologies, and we use these insights to construct FatPaths and show its advantages by a rich evaluation and theoretical analysis. Thank you for your attention. I will now take your questions.